Today we will be presenting our CS511 project, Smart Segmentation. So, what is Smart Segmentation? Well, Smart Segmentation entails finding phrase boundaries in text, and segmentation itself is not a new concept. Browsers currently do segmentation, and if you double-click a word, for example, the browser will highlight that word. Or if you triple-click a word, the browser will go ahead and highlight that sentence. So segmentation does already exist. However, the difference between the browser segmentation and smart segmentation is we want to be able to use context and highlight stuff aside from just a word or a sentence. We want to be able to highlight a phrase. So we're going to start off by giving a demo, and our smart segmentation project is a Chrome extension. So to start off, we will use Amazon on a page for Asus laptops. So the first thing we will do is segment this entry based on F511 UA. Now there are two ways to start the segmentation mode. You can either right-click and enter segmentation, or there's also a keyboard shortcut. Once segmentation mode is started, the phrase will be highlighted, and you can toggle between phrases using the up or down arrows, as seen here. And you can also use left or right arrows to toggle between segmentations of the same length, or there are shortcuts for copying as well as escaping the Chrome extension. So the first segmentation found is the word that we chose. The next segmentation found is the phrase for Asus VivoBook F511 UA FHD laptop. So this is a good phrase because as a user, this is something I could be interested in. It makes sense to me. It's something that might stand alone. Now, if we click on this page, we can then go ahead and segment something else. So here, for example, say we want to segment VivoBook. So right-click on VivoBook, and we will enter segmentation mode. So VivoBook gets highlighted as the first segmentation, then Asus VivoBook, then we go to FHD as well as laptop, and then we get the whole entry. So these segmentations are useful to the user, and the user can also copy this. So if I click enter, it will copy the segmentation and then exit segmentation mode. So now if I check my clipboard, as seen here, the entire product entry was copied to my clipboard. Now we will show it on a different site. We will show our tool being used on the Support Vector Machine Wikipedia page. So I can right-click on Vector and enter segmentation mode. Vector gets highlighted as the first segmentation, followed by Support and Support Vector Machines, all of which are valid segmentations. If we go again, we can see more segmentations, and we see that another segmentation we get is the full paragraph, which is something that might be returned by the browser, but it's also a valid segmentation, so our tool will return it. Now I'm going to go ahead and turn things over to Richard, who will talk about the approaches to smart segmentation, as well as how our approach differs from these alternative approaches.
As with any research project, one critical aspect to consider is the difficulties to be overcome and their value. Smart segmentation is no different in this respect. One significant difficulty arises from the fact that the web is intended for consumption by humans. In fact, vendors who make the same information available without a human viewing the page may suffer from additional comparison shopping, lost advertisement revenue, and possibly other negative impacts. The data on the page are therefore not typically identified for automated consumption or easy segmentation. Thus, our project has to deal with the HTML DOM tree, which, though it is constructed mostly for presentation of the data according to a standard, does contain hints about relationships among its parts. In using this data model, our project had to be careful to avoid dependence on aspects of the DOM tree that might change arbitrarily. We also considered part-of-speech tagging as a tool, but this approach is inherently limited by some of the prime targets for smart segmentation: product summaries. These summaries are rarely in sentence form, and therefore confuse part-of-speech taggers. Now let's look at the implementation of our solution. The first step in our segmentation process consists of extracting the starting text indicated by the user and some context around it. Since our segmentations will be drawn from this surrounding text, we want to limit this text to be relevant to the text selected by the user, specifically to one particular item if the user was selecting on a page with a list of items. Once the target area of the page, represented as some non-inline element of the DOM tree, is identified, we extract text content, taking care to place whitespace around elements that are not inline. When provided on the page, our solution uses ARIA attributes to better capture the meaning of DOM subtrees. To address the challenge of the browser highlighting an entire hyperlink as the target of a right-click operation, our solution modifies all hyperlinks in the document to ensure there is a span element surrounding each word of the link, giving the context needed about the user's indicated starting point.
So let's talk about frequent pattern mining. Frequent pattern mining is an algorithm that helps us extract repeated phrases based on term frequency associations between different words. Gensim, a Python package we use, actually implements frequent pattern mining and generates n-gram segmentations. This is a form of unsupervised learning because the segmentations that Gensim generates are not able to be evaluated by some sort of machine. Instead, they have to be evaluated by the user, and Gensim is just making inferences based on the collection of data it's received. A big part about pattern mining is the notion of word shape, and word shape is being able to identify patterns among iPhone 7 and iPhone 8, for example. These two terms are slightly different in that they have different numbers, but they actually should be correlated to the exact same phrase so that pattern detection can work better on identifying similar phrases like this. Let's look at an overall high design picture. We've seen an end-to-end demo of this, but now, from a technical standpoint, the UI is responsible for sending 3 pieces of data to the backend: the word the user right-clicked, the record text, as well as the entire page text, and Gensim generates any valid segmentation of the given record. It then passes it to the ranking function, which takes into account the phrase length, the number of words, as well as what the user right-clicked, to generate all the segmentations in ranked order of increasing length, as well as only the segmentations that matter to the user. And the ranking function returns all this back to the UI, and the UI displays the segmentations in increasing length order. And finally, this fourth notion of a feedback model can also be fed here into this loop that the segmentation can be copied to the clipboard, and then that gives us feedback about what is a good segmentation for the model. And the way we evaluate a model like this is actually very similar to text retrieval, because the user has to decide what's relevant and what's not. So this notion of precision and recall come into play again, where we need to rank what percentage of results returned are in the right order, as well as how many results returned are within the general order of answers. So it's very similar to a search engine, except there's actually this notion of overall accuracy that also needs to be captured, because in text retrieval, documents can sometimes be unranked and completely irrelevant. And just like some segmentations can also be completely irrelevant, the ranking function excludes that already. But there's also this notion of whether segmentations overall capture what the user wants. And that actually is captured with this accuracy metric, which we need to include in addition to precision and recall. And then also additionally, another way of evaluation is simply user feedback. What the user copies to the clipboard is what's considered the best segmentation. We also learned that user feedback is critical for model improvement, because this is an unsupervised learning problem and it needs to get feedback from the user so that the weights for our ranking function can be adjusted based on this user feedback. We also learned about the importance of having an intuitive UI to complement the data returned, and this is because the browser already does segmentation, and so our smart segmentation should complement what already exists. It shouldn't try to override the behavior by default, and instead should provide an intuitive way for the users to see, highlight, or copy segmentations that are important. For future work, we hope to incorporate the feedback model into the central server so that the central server can actually update and learn based on what the user thinks is a good segmentation. We also hope to investigate HTML DOM input further and use that as another clue to get smarter segmentations. And finally, another project that our mentor is working on, Web Data View, we would love to integrate this project with that project, because smart segmentation was trying to get structured data from unstructured data, and Web Data View is all about querying that structured data. Thank you for watching.